Okay, good morning. So today we are continuing our section on sheaf theory. We have an exercise that relates pretty heavily to complex algebraic geometry. First, to start off, then we're going into sheafification. Um, and we're going to see how far we can get through that. Um, But then yeah, we're getting pretty close, I think, to the end of this chapter. Because then we end with sheaves of abelian groups. And then we get into schemes, which um, basically gives us a broader characterization of the important things that we care about on varieties. So like a scheme is basically like the underlying set, the topology on the set, and then the structure sheaf of the set. Um, so it's kind of everything we care about bundled in one. Um, yeah, I'm pretty happy with the progress that we're making. I think that we'll need to maybe talk about a little bit of topology because we get to this whole business of a sheaf on a base or on the basis of a topology, and I don't think that Garrett has seen that material. So, just in the spirit, so today we're also going to be covering um, some stuff with the complex logarithm, which is kind of weird. So anyway, without further ado, let's get into it. Um, so let X be the complex plane with the standard topology, and then let Ox be the structure sheaf of holomorphic functions. So now I need to define a holomorphic function. Um, so a function f of u or f of x comma y is equal to u of x comma y plus I v x comma y is holomorphic if the partial of u with respect to x is equal to the partial of v with respect to y, and the partial of u with respect to y is equal to minus the partial of v with respect to x. And these are called the Cauchy-Riemann equations. This is the main focus. If you take complex analysis at JMU, this is like a good half the semester is kind of building up to these. Um, Holomorphic functions are very interesting to study, and I met a lot of kind of interesting things. So we have a structure sheaf of holomorphic functions. And then let script f be the pre-sheaf of functions which admit a holomorphic logarithm. Okay, so now we get to another important definition from complex analysis. So we define, there's two types of log functions, and I always mix up the capitalization. So I'm going to Google the capitalization. um, Okay, maybe the capitalization was just in my textbook. But basically, log z is equal to log e to the I theta, or I guess r e to the I theta, where r is like kind of the radius and e to the I theta is some kind of direction, right? So the r is the magnitude and the e to the I theta is the direction. So then the complex log is equal to the real natural log of r, of the absolute value of r, plus I times theta plus 2k pi, where k is in z. So basically, the idea here is that we get this idea of branching, right? So for each k and z, we have like a branch in the complex direction. So the principal branch is the one where k is 0, and this is typically what we're interested in. What? Sorry, there was like a weird bug on my shirt.
No, you're good.
Yeah, so this is the complex logarithm. Um, so, um, now what is the criterion for a function to admit a complex log? What is the criterion for a function to admit a complex logarithm? Function must be nowhere 0. So, i.e., f in f on u must be nowhere 0 on u. And then its contour integral for every closed curve in the domain must be analytic.
What does that mean?
So there's a bunch of complex analysis theorems that are kind of centered around this idea of contour integration.
Yep.
And that's a whole set of lectures in and of itself.
Okay.
Basically, it's that we want trying to figure out how much to explain. Have you heard of Stokes's theorem?
Not really. It sounds familiar, but
Okay. So it's this theorem in Calc 3 that says that if you have a vector field which is conservative, meaning that there exists a function whose gradient gives the vector field, um, if you have a conservative vector field, then any two paths that go to the same point do the same amount of work.
okay.
Um, and so with contour integration, when you have like a closed loop C, like a closed contour C, if F is analytic or holomorphic, they're the same word. They mean the same thing. If
Yeah.
F is holomorphic in the plane, then it basically means that we have a conservative vector field and that this integral, the integral of work along this path oriented this way, is 0.
Okay.
Where this changes is if there are divisions by 0 in the function, we get these things called poles. And if you have a pole, say at 0, it just looks like everything going up towards infinity at 0. And so naturally, integrating around this closed contour, um, then the integral, if there were a pole in this function,
Yeah.
would be equal to 2 pi I times the sum of the residue of f prime of z over f of z at the pole. And so what's the residue at a pole? Well, that's a whole nother thing, but
Mm-hmm.
not terribly hard to define. The idea is that, like, you kind of break the integral into the parts where the work is 0, and then the
Mm-hmm.
poles.
Oh, okay.
And so yeah, it's an extension. So this is done by the Cauchy-Goursat theorem, and then Cauchy's residue theorem is this one, and that's kind of like the big point of complex analysis. Um, but what we're saying is that if f of z is nowhere 0, um, then as long as this function here is analytic, or is holomorphic, the way we've defined it, and I'm just
Yeah.
going to go ahead, or analytic. As long as that's analytic, then basically by the Cauchy-Goursat theorem, this is 0. Um, so for it to admit a complex logarithm, this is our criteria. So then the actual problem, now that we've done all of the setup, is that we should describe an exact sequence of pre-sheaves on X, or the complex plane, 0 into the constant sheaf on Z, into the structure sheaf on C, into the sheaf or into the pre-sheaf of holomorphic functions on C, which emit a complex logarithm, into 0. And I'm going to make this O nicer. I'm going to make that C nicer. So,
What's the underlined Z mean again? I'm sorry.
this is the constant sheaf.
Okay.
And it's not, we showed that it wasn't actually a sheaf, it just gets called a sheaf. If it's locally constant, then it is a sheaf, but I don't think it's meant to be here. This is an inclusion, and then this map here from the structure sheaf on C to script F is given by F gets sent to e to the 2 pi I F. And then, so this is part 1. Part 2 is to show that F is not a sheaf by failing glueability. And the hint is local log existence is not the same thing as global log. So I think we've spent enough time setting this up that like we should do this. And I was kind of looking at it for the 10 minutes before we logged on. Um, and I was kind of like, this sucks. But then I was like, actually, this is one of the cooler applications. Like, this is one of the few times we get to see an application of algebraic geometry. So,
Yeah.
um, um, so, um, yeah. First, let's describe this exact sequence. So, this is by the inclusion map. I have, z is equal to z. And I guess maybe it's mapping z gets mapped to z. Um, so, yeah, I guess we'll define, let's call this phi, let's call this psi. So, I think, let me recall. The underline thing. I'm pretty sure it's the constant sheaf. Um, yeah, it is the constant sheaf. Yeah. Um, yeah, so it's just that every open set is equal to Z. So every section of Z underline U is equal to Z. Um, so yeah, we're gonna send F phi U. Um, or no, we're sending sections. So phi of Z is equal to Z contained. Well, this is the sheaf of smooth functions. Smooth functions. How do we send? Oh, I guess we're getting this sent to smooth functions in C infinity over Z. Um, which I'm kind of wondering if this is the empty set. Because I can't think of anything that's smooth over Z. It's just not possible. It's not differentiable. So I guess this is equals empty set. And then for psi, we're taking we'll call it we're taking a section of functions on an empty set, or on a set, and then we're sending this to the collection of e to the 2 pi I f such that f is in C U. And it's worth noting that this is an injection by the construction. It's injective. And so then, so this is, the empty set is both imphi and cursi. And then, so our sequence, we'll call this A bullet, is exact. And I think that works out pretty nicely. There was always, of course, the possibility that I've done something horribly wrong. Excluding this possibility, unless you see anything blatant.
I don't see anything blatant.
We want to show that f is not a sheaf by saying that global logs. Okay. That global logs might not exist. So we want to take the gluing axiom. We want to find UI, UJ with FI in script FUI for all I such that or FI restricted to UI intersect UJ is equal to FJ restricted to UI intersect UJ for all I and J. And it's not want to find, but given this, given this, show that we can't find some F. Show that F in the section over U such that the restriction map of F to UI is equal to Fi for all I. So, cooking up this example, um, we want to find. So this is the sheaf of holomorphic functions which admit a log, or the pre-sheaf of holomorphic functions which admit a log. So they're nowhere zero. So Garrett, do you have any ideas?
I I don't. Does it go off the fact that like the smooth functions in C infinity over Z are the empty set? Like we can't find any?
Well, I don't know actually how it relates to the whole exact sequence business. Um, I don't know. Let me think. I mean, we just have to show that, like, there's some function which disagrees. I think the hard part is choosing. First, let's lock down. Let UI be the ball around 0 of radius 1. Let uj be the ball around 0 of radius 2. Because what this does is in the complex plane,
Mm-hmm.
this gives us what? I did not draw a polygonal shape that badly. Okay, there we go. I was gonna say, like, that's offensive, man. um, yeah. Wait, what? Why is that the thing that you're editing? That's very dumb. Whatever. You can imagine that that's there. So, so this is like a visualization of what we're working with.
Mm-hmm.
Um, and so we want to find something that maybe like has like the same behavior in here. But then as soon as we get out here, it splits off into two things.
Okay.
Um, because they agree on the intersection, which is the first which is UI. And so we want what are good? I just can't think of functions that emit logs that are nice. So we want something where it's nowhere 0. So maybe like e to the x plus I e to the x. Is that analytic? Um, yeah, that's analytic. Guess anything in one variable. No, it isn't analytic. This would be e to the y. There we go, because ux equals vy, and then minus uy is equal to vx. Yeah. So this is one function. Doesn't it admit a nice log? Yeah, it does. Um, and then we maybe want I don't know. I'm having trouble cooking up a function.
Mm-hmm.
I think we have the picture. I think that that's fine.
Yeah.
The idea is there.
Yeah.
If I think of one later, we can come back to this.
Okay.
Okay. So, all right, properties determined by stocks. We now come to the second way of understanding sheaves mentioned at the start of the chapter. In this section, we will see that lots of facts about sheaves can be checked at the level of stocks. We call any property determined at the level of stocks stock local. This isn't true for pre-sheaves and reflects the local nature of sheaves. You'll see that sections and morphisms are determined by their stocks, and the property of a morphism being an isomorphism may be checked in stocks. So theorem. Sorry, I have like the really annoying thing where the page of the book won't just stay down. There we go. Right, now will we work, hopefully. So sections are determined by germs, i.e. f of u mapped to the product p and u of stocks is injective. So yeah, this is I guess okay. He gave 2 hints. Hint. Use identity axiom of sheaves. not glue. So now, I'm pretty sure I remember the identity axiom, but let me just write it down from the definition so we don't waste time. Okay. So for every open set U, if UI covers U, and F1 and F2 are in the section on U, and F1 restricted to UI is equal to F2 restricted to UI. For all I, then F1 is equal to F2. Oh yeah, that definitely motivates injectivity. Yeah. So proof, let UI cover U. Basically we get identity, and then I want to define this map phi of phi from the section on U to the product of stocks by phi of a function should go to, I guess, all of the vanishings. Oh, it's germs. Duh. Wait. It's all of the pairs of F comma UI such that P is in UI and F is in section on U, and it is not just this thing, it is the product for P and U. Wait, no, it's not. I'm dumb. That's fine. It's just that thing. No, maybe it is the product. Damn it, maybe it is the product. So dude, I have Gracie Abrams stuck in my head.
That's rough.
It's I don't know why. It's like the only thing that could make me focus yesterday. And normally I listen to like technical death metal. And like yesterday my brain was like, no, white girl music now.
White girl music. It's
Dude,
a
it's
dangerous game.
crazy. It is a dangerous game. Anyway, um, yeah, so I guess we should have F is not, yeah, no, okay, I think that's fair. I think that this is, and so then we want to pick prod FI UI. Like, this is just a bunch of local rings. This is a product of local rings, which is basically the structure sheaf.
Right.
If it weren't defined as, yeah, how is this not the structure sheaf, actually? Maybe that's the point of the proof. Then UI is equal to UJ, and F is equal to G. Um, Phi inverse of G UJ is equal to um G and F UJ phi inverse of F. Um, but UI equals UJ implies F equals G by identity on boom. Okay, that's the proof. And this generalizes, of course, for products. I didn't do it that way, but like if we did it for products, it would work.
Okay.
Um, um, so an element SP, P, and U of germs in the product over P and U of FP, SP is equal to the product consists of compatible germs if for all P in U there exists a representative SP tilde in F over UP open in U for SP such that the germ of SP tilde at all Q in UP is Q. Definition that's nicer that we're going to use instead. There exists UI covering U sections FI in script F UI such that if P is in UI SP is term of FI at P. Remark, any section S of F over U gives a choice of compatible terms. Theorem and a choice of compatible germs for a sheaf of sets or F over U is the image of a section of F over U. And this makes sense basically by construction. Like, it uses glueability to prove it, and it probably sounds tedious to prove, in my opinion. So I'm gonna omit it. But, like, it makes sense with how we define compatible terms. It's just saying that we can choose an image of a section, or we can choose an image of compatible terms. This perspective motivates the agricultural terminology sheaf. A sheaf is a bunch of stalks bundled together appropriately. Yeah. So as a theorem, morphisms are determined by stalks, i.e., if phi1 and phi2 are morphisms from a pre-sheaf of sets F to G, pre-sheaf of sets to sheaf of sets that induce the same maps on each stalk. Phi1 is equal to phi2. Hint. So we have by previous lemma an injection here, since G is a sheaf over U. And so then we want to let this be phi1 and this be phi2. And then we want to show that they're the same thing. So if they induce the same maps on each stalk, so basically we're saying that these two things are equal. And maybe we'll call these so we want to start with let F in the section on U get mapped to its product of SP. And we'll call this F prime and FP. But then this goes equivalently to phi 1 of F prime equals phi 2. So F prime is equal to GP product GP in the stock G. But then there's an injection to these things. So then, so if these two things are equal, then they have a preimage through this map. Let's call it I. So then I inverse of phi 1 of F prime is equal to I inverse of phi 2 of F prime. Equal to phi 1 of F is equal to phi 2 of F. And there we go. That's the proof. Diagram chasing. Gotta love it. Yeah. Okay. Theorem in a similar way, isomorphisms are determined by stocks. And so basically, if this is an isomorphism down here, then it's both a unique isomorphism and it's determined by stocks. And then theorem, none of these are true for general pre-sheaves. Let's take a 5-minute break and then come back for sheafification.
Okay.
So be back at like 8:36.
Okay.
Okay.
All right.
Yeah. Okay, so sheafification. Every sheaf is a pre-sheaf, just as groupification gives an abelian group that best approximates an abelian semigroup. Sheafification gives the sheaf that best approximates a pre-sheaf with an analogous universal property. So definition, if script F is a pre-sheaf on X, then a morphism of pre-sheaves on X is a sheafification of F if that's a sheaf, and for every sheaf G and any pre-sheaf morphism G from F to G, there exists a unique morphism of sheaves F from the sheafification to G, making the diagram below. G so we have to show that it exists. The following two exercises require existence, which we will show shortly, but not the details of the construction. If it does exist, it exists. It is unique up to unique isomorphism. So theorem. So if exists, it is unique up to unique. So, remark. Sheafification is a functor. From pre-sheaves to sheaves. So from pre-sheaves on X to sheaves on X. Meaning that we take over objects and morphisms. So we have like pre-sheaf morphisms here. So this is a sheaf morphism. This is a pre-sheaf. This is sheaf. This is a pre-sheaf morphism. This is a sheaf morphism. This is a sheaf. This is a sheaf morphism. And so then this gets sent to this. That's the object getting sent. This is the morphism that gets sent. And it's a functor. So constructing existence. Every pre-sheaf of whatever, of something, has a sheafification. So let script f be a pre-sheaf. Define by the section over U is the set of compatible germs or compatible families of germs of F over U. This is equivalent to saying the set of all FP in the stock P in U such that for all P in U and S in F over V with SQ equal to FQ. Nope. Hold on. That does show up later, the definition, but I jumped a line. For all P and U, there exists an open neighborhood. Open in U such that S is in F over U. No, S over V. With F Q equal SQ for all Q and V. So basically everything that we can get to agree forms a sheaf.
Yeah.
So basically everything that can agree in pre-sheaf goes into sheaf. And then this is clearly a sheaf because of like restriction maps kind of gluing things together. Show that the map SH satisfies 2.4.5. This satisfies the universal property of sheafification. So this is the universal property of sheafification, right?
Okay.
Yeah. Show that the sheafification functor is left adjoint to the forgetful functor from sheaves on X to the pre-sheaves on X. Damn it, that is a useful exercise. Okay. So theorem SH is left adjoint to trying to come up with like a forgetful functor, but whatever, forgetful functor from sheaves to pre-sheaves. Okay, so left adjoint. I don't remember enough of that section as I should. Yeah. I.e. there exists a natural bijection for all A in sheaves and B in pre-sheaves. No, I'm just going to call that F, such that tau AB is defined from the morphisms of pre-sheaves of SH A to pre-sheaf to the morphism of sheaves A to the forgetful functor of B, except that doesn't make sense. Sheaf goes from pre-sheaf. Damn it, I switched them up. F SH. There we go. Okay. And that. Wait, no. Now it switched up. God damn it. This is the right adjoint. This is not right. It should be SHF, but then we switch A and B. B, A, B, A, and then we switch sheaves and pre-sheaves. And now, there we go. And now this is the left adjoint. And then as a corollary, we don't need to sheafify to take a kernel, but we do need to sheafify to take the co-kernel and the tensor product. Yeah. Damn, we've done good progress today.
Yeah.
And then as a theorem, the sheaf F to the sheafification of F induces an isomorphism of stocks Wait, no. This is a map of pre-sheaves. As a map of um I don't know if I want to prove this. Just my brain is feeling tired, very fatigued. Um, I'm gonna bump this to prove it off camera later today
Okay. Huh.
because I think I will need to maybe take more time on it. It might not even be that hard. I'm just tired.
That's fair.
And there's a lot of definitions coming up, so I'm thinking like, oh, well, we can just get through the new definitions. Um, because yeah, so this next section is section subsheaves and quotient sheaves. From the perspective of stocks. So the theorem let phi from script F to script G be a sheaf morphism on sets on a top space X. Then the following are equivalent. So phi is a monomorphism in the category of sheaves. Phi is injective of between stocks phi p from a stock to a stock for all p in X. Phi is injective on open sets. Phi view from section on U to G on U for all U open in X. I kind of want to just write down the definitions and then do the construction either tomorrow or off camera because I'm tired. I'm tired and I don't think anybody's watching this. Although my subscriber count does keep going up, and I'm really curious if people are watching this.
I was looking at the views the other day, and it's funny, like the first one is a lot of views, and the views kind of go down as we go through it.
Yeah, but
Could
I
also
mean,
be like how recent.
it's kind of funny. I've gotten like random people subscribe. Like I had a few people from my topology class follow because I'm doing this algebraic topology seminar as well.
Yeah.
Um, but like, yeah, I had a few random people from a few random universities follow. So I don't know. Maybe they're
Wow.
watching it. Um, yeah. Um, so if these conditions hold, then this is the definition. F is a subsheaf of G. Um, so yeah, that's a definition. And then continuing the notation of this theorem, the following are also equivalent. So A, phi is an epimorphism in the category of sheaves. And then phi is surjective on stocks by phi p from fp to gp for all p and x. If I, well, if these hold, then phi is, or no, sorry, then G is a quotient sheaf of F. And so yeah, it would be kind of remiss to not give an example, and so we'll end with an example, I think. This was everything that I wanted to get through today. Because that actually just leaves us 2 sections left in chapter 2, and then we're on to schemes.
Wow.
So doing good. So example, let X be the complex plane with the standard topology, structure sheaf of homomorphic functions as defined in the first exercise from today. Let phi star, or I keep saying phi. There's not a phi here. O star of x be the sheaf of invertible nowhere zero functions. Holomorphic functions. Then this is a sheaf of abelian groups. Abelian groups under multiplication. Then we have a map into z of the constant sheaf times 2 pi I into the sheaf of holomorphic functions. Into 1. And what the hell does sheaf 0 or sheaf 1? What is 0, 1 sheaf? They are supposedly isomorphic. That this is an exact sequence. I'm going to call this C dot. So claims C dot is exact, called the exponential exact sequence. And they actually, Vakil bumps this off. Zero is isomorphic to 1. I'm really confused. I guess it's that, oh, since it's sheaves of abelian groups, then they're trivial groups. So this is the trivial group 0, and this is the trivial group 1.
Oh, okay.
Zero is 0 object. 1 is just E. And I'm gonna guess that this is the surjection and this is the injection. Yeah, that's the surjection, that's the injection. Yeah. And then yeah, as a result of this, according to our definition, OX star is the quotient sheaf of OX because it's a surjection. No, It's a surjection of stalks. So it's not actually quite a surjection. And it might not be an injection either. So not a surjection of sheaves, but of stalks. And then similarly, C bar is a subsheaf of ox. Not sure. Okay, and we'll open up tomorrow with this example.
All right.
But otherwise, I'm pretty happy for today. Tomorrow, we'll try and get through recovering sheaves on a base. And then on Friday, we'll get to end the week with sheaves of abelian groups form abelian categories.
All
Oh
right.
no, I was wrong. There's more. So we'll finish chapter 2 on Saturday.
Okay.
That's pretty good. That's pretty great, actually. All right. Thank you, everyone, for watching. Yeah.